Exponential and logarithmic equations. Solving exponential equations using logarithmic form. First, we'll rewrite the equation with the term containing the exponent by itself on one side. This is actually a subpoint. If there is a coefficient of that term, you need to divide by that coefficient. So the first two steps really is isolating the exponential expression. We'll change the new equation to logarithmic form then, and then solve for the variable. Example 1, solve the equation 3000 equals 150 times 10 to the 4t. First thing I'd like to do is for us to identify the exponential expression so that we can isolate it. The exponential expression is simply the base with its exponent. The 150 out front is a coefficient. It's not a part of the exponential expression. So the first thing that we'll do is to divide by 150. So we get 20 equals 10 to the 4t. So now we're at the point where we can change to logarithmic form as stated in the directions here. So we'll use log. The base is 10. Remember, a log is an exponent, so your exponent here is going to be set equal to the log, and the argument of the log is 20. To completely isolate t, we divide both sides by 4, so we get log of 20 divided by 4. Now we can put that into the calculator. The log button on your calculator here is base 10. So log base 10 of 20, close your argument, and divide by 4. And we get about 0.325. Let's solve the equation graphically to confirm this solution. So we can go to the equation editor and put 150 times 10 to the 4x. And the other side of the equation is 3000, so we enter that as its own value. Just a standard zoom is not going to give me the graph for the second equation. It's y equals 3000 is quite a ways up there. So we can do a zoom fit, and then you'll see that horizontal line. Alright, now we'll go second, calculate the intersection, enter, 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 and we get about 3.325. Example 2, doubling time. Suppose $2,500 is invested in an account earning 6% annual interest, compounded continuously. How long will it take for the amount to grow to $5,000? Let's remember our interest that's compounded continuously formula. P(e) to the RT is the ending amount. Our principal is 2,500. E to the rate is 0.06. T is what we're solving for. And the amount we want to end up with at the end is $5,000. We're trying to find the time that it takes to double our investment. So the first thing that we do is to isolate the exponential expression. That is simply the e to the 0.06t. We're going to divide both sides by 2,500. e to the 0.06t equals 2. Now we've come to the end of what we can do in exponential form. Let's change it to log form. So our log has base e. We're going to use natural log since it has base e. Remember, a log is an exponent. Your exponent is the 0.06t. The argument of the log is 2. We're going to divide by 0.06 on both sides so that we can isolate t. Let's put this into the calculator. Natural log is right here. Oops, let's go to home screen. Natural log is right here of 2, and divide that by 0.06. So I get about, let's say, you get about 11.6. So how long will it take for the amount to grow to that? About 11.6 years. When we're using the PERT formula for investments of money, time is always in terms of years. Change of base formula. We can use a special formula called the change of base formula to rewrite logarithms so that the base is 10 or e. If the base is greater than 0 and the base is not 1, a is greater than 0 and a is not 1, and x is greater than 0, then the log base a of x is equal to the log base b of x divided by the log base b of a. You can change the base to be whatever you want. You could make it a base 2, you could make it a base 17 as long as it follows these constraints. If we want to be able to use our calculator buttons, we would change it to the common log, base 10, or the natural log, base e. So for logarithms that are in example 3, we can use this change of base formula. Let's evaluate log base 8 of 124. According to the change of base formula, log base 8 of 124 is equal to, this time let's change it to log base 10, log base 10 of the original argument divided by log base 10 of the original base. Then we can put this into the calculator. Log 124, make sure to close that argument, divided by log of 8. And we get about 2.32. Let's try evaluating this log. Log base 25 of 0.00478. Let's go ahead and change this one to natural log. Again, we could change it to the common log with base 10, or we can change it to natural log. Just for variety, let's go ahead and change it to natural log with base e. So it'll be equal to the natural log of the original argument of the log divided by natural log of the original base of the log. Let's put this into the calculator now. Natural log of 0.00478, close those parentheses, divided by natural log of 25, and close those parentheses. So we get about negative 1.66. Most graphing calculators are also going to have a log base function. So we can go back and evaluate log base 8 of 124 and use the log base button in the calculator instead. In the TIs, this is found by pressing the math button, and if you scroll up so that you're scrolling up from the bottom, so it's way down there, there's your log base. Gives us a template, so I'm going to put in the base as 8, the argument of the log as 124, and enter, and you see the same answer as we had when we evaluated with the change of base formula. Let's try this one. We could take math and log base and base 25, and the argument is 0.00478, and you get the same as we got before using change of base formula. So don't forget the change of base formula, but remember also you have that log base button that you can use in order to evaluate in case you have a calculator that does not have that function. Example 4 is investment. If $10,000 is invested at 10% compounded annually for t years, the future value is given by S equals $10,000 times 1.10 to the t. In how many years will the investment grow to $45,950? Well, we can start out by rewriting the formula that was given. Okay, and they want to know when that investment will grow to $45,950. So that means when will S be 45,950? To solve this by hand, we're going to divide both sides by 10,000 so that we can isolate the exponential expression. Of course, that gives us 1.10 to the t on the right side, and on the left we'll get 4.5950. Now we can go ahead and change this to logarithmic form. So we have a log. The base is 1.10. Remember, a log is an exponent. That exponent is t. And the argument is 4.595. So let's put this into our calculator. It's going to be log of 4.595 divided by the log of 1.1 if we use the change of base formula. So t is about 16 years. Again, you could use the change of base formula, or you can use the log base button in your calculator. Let's put this into our equation editor as well so that we can confirm the solution there. We have 10,000 times 1.1 to the t, and we have 45,950. There we go. And let's set our window from 0 to 25 just so we can try and capture where that happens. Let's do a zoom fit so that we find that window that shows the intersection, and we will calculate the intersection, first curve, second curve, and guess, and we can see the same answer at about 16 years. It'll be $45,950 in that account. Let's solve this logarithmic equation here by converting it to exponential form. So similarly as we did the exponential equations where we isolate the exponential expression, we're going to isolate the logarithmic expression here, and that is simply log base 3 of x. The 4 is a coefficient that we need to divide off. So when we divide both sides by 4, we have log base 3 of x equals -2. And we've come to the end of what we can do with logarithms. We've isolated the log. So let's change to exponential form. Exponential form is going to be the base 3. Remember, a log is an exponent, so your exponent on that base is -2 equals the argument of the log. We're going to get 1/9 there. Again, let's verify this solution graphically. Go to your equation editor, type in 4 times the log. This is a base 3, so we're going to go with either using the log base button, or you can use your change of base formula. Log base 3 of x, and the right side of the equation is -8. So let's do a window from 0 to 5 and zoom fit. We definitely see the intersection in the window, so we calculate the intersection and we get 1/9 as the x. So graphically, we would be given a decimal approximation of 0.11. Example 6 is sales decay. After the end of an advertising campaign, the daily sales of Genapet fell rapidly, with sales given by S equals 3,200 times e to the -0.08x dollars, where x is the number of days from the end of the campaign. For how many days after the campaign ended were sales at least $1,980? So let's go ahead and copy down our formula, 3,200 times e to the -0.08x, and we want to know when that reaches 1980, and then we'll look at our graph to see when that happens as an at least situation. So 3,200 times e to the -0.08x, and then we have 1,980. If I set my window to go from maybe 0 to 20, we can see the first 20 days after the end of the campaign. It does say that it fell rapidly, so hopefully we can find the intersection of those two graphs in the window. We'll do a zoom fit, and definitely we see the intersection. So let's calculate that intersection. And you see there, at about 6 days, our sales have declined to 1,980. So for how many days after the campaign ended were the sales at least $1,980? For 6 days. After the 6 days, our sales are going to decline. There we go. Get on that trace there. You can see after that the sales are going to be falling below the 1,980. Example 7 is an example of cost benefit. The cost benefit equation, natural log of 1 minus p equals -0.0034 minus 0.0053t, estimates the relationship between the percent reduction of emissions of carbon dioxide, P, as a decimal, and the tax, T, in dollars per ton of carbon. What tax will give a reduction of at least 50%? So we're going to say the natural log of 1 minus 0.5, we're reducing by 50% there, is going to be equal to -0.0034 minus 0.0053t. If you like, we can go ahead and put this straight away into the graphing calculator to solve. We'll have natural log of 0.5 and negative 0.0034 minus 0.0053x. Let's set our window from, well, 0 to 100 and see if we can find the, with a zoom fit, see if we can see an intersection. Looks like we're going to have to go more to the right. So let's set the window at 0 to 200 and do a zoom fit. And yes, now we do see that. So let's get the intersection of the two graphs. And there we are. We get a reduction in which variable is your the tax dollars. The tax dollars is going to be your x. So $130.14, and that's the tax per ton of carbon, and that is going to give you the cost benefit of cost of $130.14 per ton of carbon will reduce the emissions of carbon dioxide by at least 50%. And that does it for this section, so go ahead and try your homework. Let me know if you have any problems.